Hooray, naming! So yeah, here's all our rules, again summarized out. I did kind of highlight the big stuff up at the top, our acids and our esters. So those are going to be the most relevant for naming in this particular unit. We'll talk, or I'll look at a couple examples here in just a second, and we'll address some other kind of subtleties of the derivatives, because while you're not explicitly responsible for naming all of them, you will see their names pop up, so it can be useful to have a sort of understanding of it. Okay? One of the things that is kind of nice about these, or naming within this unit, is that we're at the top of the priority list, which means the suffix is going to either be ic acid or O8. Okay? So to give you a kind of a sort of idea on what's going on with the origin of those, the ic acid is kind of standard. Okay? So there we go. We're now referencing the carboxylic acid functional group. But what's going on with the O8 name? Well, you've seen the O8 name before, right? With a negative charge there, sodium benzoate, right? It was the soluble, water-soluble form of benzoic acid, and so we called it sodium benzoate. Well, that's really what's going on with our esters, okay? If it was sodium benzoate, all we were saying was that sodium was connected to it. If I move to an ester, it's no longer a sodium, and it's no longer an ionic bond, but thankfully the name stays relatively the same. Now I have one carbon connected at that acid position, if you will, and it becomes methyl benzoate, okay? If we had a phenyl ring over here. And what if we had two carbons? Well, now two carbons is ethyl, so it becomes ethyl benzoate. So when we're looking at the ester or even the acid name, really what we're doing is we're naming that core structure, and we're now differentiating what that next piece is. Okay, if it's a hydrogen, that's an acid. If it's a carbon, now it's an ester. We're still naming kind of the core part of your name. Very, very similarly, it's that benzo piece, okay? And the benzyl was just, or benzo, I should say, was just an example. It can be really any kind of primary chain, as we'll see here in our next examples. So if we were to go through and provide the name for these things, you should be able to go through and break it down similarly. Okay, so I will do the top two. I'll name the top two for you, and then I'll leave you to kind of process through the bottom two, which are a little bit more straightforward, but I'll kind of highlight the aspects that would be super important. So let's go ahead and take a look at the top two examples. We start with the first one. We've got 2 carbons. If it's 2 carbons, our root would be F. Okay, we are looking at an, okay, because it's just sp3 kind of carbons in the backbone. So that would be our hybridization, and then we would note that our functional group here is that carboxylic acid, and so we could call it ethanoic acid. And there we go. There's the name of that substance. One of the reasons why I put this one on in particular is that some of you may be looking at that and being like, but Mike, it's not called ethanoic acid. And go, well, yeah, it is called ethanoic acid. It is also called acetic acid. And for those of you going, oh my God, nomenclature is so dumb. Why would anybody ever do this? What is the name for that compound? Yeah, I bet you said water, not dihydrogen monoxide. Okay, there are certain compounds that are old enough or studied enough that people came up with names for those compounds before we had a decent naming system. Okay, and then that means that those older names are kind of carryovers or artifacts of that older system. And if we look at the water example, dihydrogen monoxide, we're not going to get rid of the common name water. It's just not going to happen. Right? The same thing is going to go for a lot of these other structures that have these common names. So be kind of aware of that. You are not officially responsible for common names. If I use common names, particularly on an exam, I do also try to provide the structure so that you don't have to know the naming, which is a whole kind of another can of worms. So what you are responsible for is being able to process through according to the IUPAC rules for how to name. Common names you're not responsible for. Okay. We move to the next one. Okay, that one's significantly more complicated because we've got a bunch of different things going on in here. Okay, we definitely have that carboxylic acid. We also have an alkene, and we also have that carbonyl. Okay, this carbon, that blue carbon, is also an interesting one because it's a branch point. So we have to decide which way we're going to go through and number this. This structure is actually organized in this fashion for a couple big reasons. The first reason is that most students are going to go 1, 2, 3, 4, 5, 6 and read right to left. Let's try that again, left to right. Okay. There are some students that are going, but I remember Mike saying that I shouldn't number things from left to right as a reflex because on a multiple choice test, the test writers know that that's what people are doing. So I'm going to number it the other way, 1, 2, 3, 4, 5, 6, okay? Which is not a bad reflex, okay? But again, you're now saying that you know what I know. But can't I just say, I know what you know that I know that you know? And it starts into this big kind of mess, side screaming different directions, okay? So you can use cheats, if you will, by kind of just real quickly swapping the numbering, but you do need a process behind it that's a little bit more structured for things like this. And in this case, that numbering that we went through left to right and the numbering we did right to left were actually both wrong, okay? And they're wrong because we need to start numbering with our highest priority functional group, which is the carboxylic acid. So 1, 2, now the question is which direction do we go, left or right? We should be going to the right, both because of the alkene and because of that carbonyl. Okay, so what we're looking at for a core structure here is actually a bute. Okay, extra challenging because all of our other numberings said the other direction. But again, those numberings aren't correct because of where the highest priority functional groups are located. Okay, before we continue to our final suffix, we do have to acknowledge that this is a butene because we have that carbon-carbon double bond in the backbone. It does fall at position 2, so I could call it but2-ene. Okay. The last part, I have the carboxylic acid at position 1, and this would be an oic acid. Okay. For those people being like, do I need to explicitly show this? Okay. Does that have to be explicit? No. My understanding is that IUPAC insists that it's explicit, and everybody has kind of universally said, no, we're not listening to you. Nomenclature rules only work as far as people use them. Okay? Common names. Again, this is why I think nomenclature is stupid to teach. Okay? But neither here nor there, but2-ene 1-oic acid. We do have to address our substituents. Okay, so I circled the 3 carbons out here, so that would be a propyl. And then the aldehyde would typically be a very high functional group or high priority functional group, and we would end with the al ending, as we learned in the past unit. But again, the carboxylic acid is a higher priority, which means we have to use the lower priority naming for the aldehyde, and that's oxo. Okay? If we're going to look at alphabetically how we'd put this together, oxo comes before P, so we'd have an oxo, and I'm intentionally leaving spaces here, propyl but2-ene 1-oic acid. We do need to specify where those things are found. The oxo is found at position 4, the propyl was found at position 2, and we'd now have our huge, glorious, awesome name. Whoop-de-doo. Except, of course, we'd still be wrong because that alkene does exhibit cis-trans isomerism, and because of that, we should also include out at the front, at position 2, our double bond is the cis isomer, and on Z, same side, it is actually 2Z, 4-oxo, 2-propyl, but, 2-ene, 1-oic acid. If you need help assigning cis and trans or Z and E, there are other nomenclature videos that you can either reference from me or from other people that look at that a little bit closer. Okay, and we've now named the top two, which means I'm going to leave the bottom two for you, but I am going to draw out some kind of hints. Our kind of primary structure includes the carboxylic acid. Okay, so here's our primary structure for this one. And what we're naming is that this piece and this piece as substituents on that primary structure. Okay. There was a sudden flash. Oh, note that in each of these cases, we went carbonyl on the left, oxygen on the right. Remember, organic chemistry is a three-dimensional system. It could have just as easily been carbonyl on the left, oxygen on our carbonyl on our right, and the oxygen on the left. The naming still holds as those is the core structure. So the core name, the root name, includes the carbonyl. Okay? The other thing to address, which we did note in both the cases up above, is that the carbon of the carboxylic acid counts in your total. Okay? That's part of your root name. Okay? Yay, nomenclature. Super exciting. Practice it a little bit and you should be okay. There are some kind of random things that might pop up. So I just want to kind of address these. If we take a look at those top two cases, those are technically amides, and I'm not saying you're responsible for them. Right? You should be able to, based off of some of the rules that we've talked about, come up with a ballpark guess on them, though, because we said we need to include the root. So there's our root. That had 2 carbons. So we'd be looking at an ethan, and it's an amide. So we'll call it ethanamide. Okay? But that doesn't address that floating CH3. Okay? Or these 2 floating CH3s. Okay? And this is where I'll get people saying, well, then it's not an eth. There's 3 carbons. It must be a prop. Okay? Remember, the longest carbon chain must be a continuous carbon chain. That nitrogen breaks the carbon chain. The methyl is not part of our backbone. Okay? That is a substituent on it. If it's a substituent, I just name it. Methyl ethanamide. Okay? Where's the methyl located? At which position is that methyl? With a structure this simple, there's really only one place to put it. Okay? It would have to go on the nitrogen. If it went on the carbon, the CH3, it wouldn't be ethanamide, it would be propanamide. Okay? But we should be explicit behind it. How do I number that? Well, there's kind of your answer. You don't number it. Okay? We don't have a way to number it because the numbering is the carbon backbone. The methyl is not connected to a carbon, it's connected to the nitrogen. So why don't we just say it's connected to the nitrogen? And that's exactly what we do. So that becomes N-methyl ethanamide. Right? If we look at the other one, and I'll switch it up with the common name, this core piece here is often referred to as an acetyl. This is where we had acetic acid in that previous case. So we could call this acete, and then we kind of throw in that core, acetan, no, I'm getting a different name confused in there. We've got acetamide, which I think is the right way to say that. We have the methyls. So we have 2 methyls, so we'll still use the dimethyl acronym, but we now have to specify the location for each of those methyls, and it becomes NN dimethyl acetate. acetamide. Acetamide, I think I got it right there. Okay. So you might see that NN reference. That's just saying there's a carbon chain coming off of the nitrogen in a higher priority functional group than amine. Than an amine. Right, too many vowels. The last one I'll kind of address is down at the bottom here. What we're looking at in that chemistry. Okay, we saw diketones before, which directly affected the acidity of that position. This is not a diketone though, okay, because we have an oxygen there. There's no acidity to address. What this really does is it sets us up with a really good leaving group out 1/2. So what we'll refer to this as is acetic, because again, let's go through and circle that. We have the acetic core, okay, but now that inner functional group, trying to get my color coding right, that inner core is an anhydride functional group, so we can call it acetic anhydride. This works out really well if we have a symmetric anhydride, and typically we do because asymmetric anhydrides aren't the easiest to go through and synthesize, okay? But they can be done. That's a nomenclature can that I don't want to open right now, okay? But that anhydride name you'll see pop up, and you'll very often see it as acetic anhydride because we're looking at simpler structures, okay? With that, hopefully we've covered all of our core nomenclature. Actually, I do have a little bit more here. If you remember that whole tosylate stuff we talked about, that TS, okay, which tends to give people a bit of issues because you forget about the tosyl on what that meant. So this was our whole tosyl. Okay? If we went through and replaced that squiggle with an OH, okay, that meant that was toluene sulfonic acid, okay, which means it acted as an acid. And if we go through and look at that, that looks an awful lot like a carboxylic acid. Okay? And so what ends up happening is that we will see the tosyl come back, but with that OH functionality, because it's now, well, a carboxylic acid. Okay? And we saw, I believe, this abbreviation also, or some of these abbreviations in some of our other sections, are sulfonyl chlorides or sulfonyl acids. Okay? If we swapped out that Cl for an OH, we can look at it as a carboxylic acid, or we could look at it as the acyl chloride or our chloride form of that structure. Okay? There are certain chemistries available to these that are just like the acyl or the acid derivatives, but it's instead of a carbon, we now have that sulfur. These structures typically show up as either acids or as protecting groups, and because they've got a lot of moving parts, not really moving parts, but bigger pieces behind them, we tend to abbreviate them based off of that TS, TF, or MS. It's not really nomenclature, but abbreviation system, kind of a common name. So you will see those pop up. Again, the primary focus behind them is really looking at that secondary piece. If we're looking at MSCl, TFCl, or TSCl, chlorine we know is a good leaving group, so it withdraws electrons. What does that mean? That means the remaining piece is going to be acting as an electrophile. So I don't really need to know what the exact structure of the trifluol is, right, or the tosyl or the mesyl. I just need to know that if I have that chloride there, that piece is going to act as an electrophile. Okay? Similarly, if we went through and instead of it being Cl, whoops, got a little bit of race happy there, but we had OH, well, now what we need to know or remember is that the functionality here is now that hydrogen, and that hydrogen is now acidic. Okay, so it's recognizing those patterns behind it to help us kind of apply. Okay, we've got some kind of reaction mechanism shown below, so you can see that and apply that. I'm not super concerned about that aspect of the mechanism, at least. Okay. And then lastly, we have a real quick overview. The carboxylic acid does bring in some kind of interesting pieces to the spectroscopy picture. Right? So with IR, we have that carbonyl and we have the OH. And I'm still commonly seeing this with IR, and I see it across the board in all classes or all versions of organic chemistry, is that people use IR to identify functional groups. IR does not identify a functional group, it identifies a bond. Once you have a combination of bonds, you now have a functional group. So kind of keep that in the back of your mind and don't start over jumping things. Okay. That said, the carboxylic acid, the conjugation of those two functional groups being so close to each other, drastically changes the chemistry of that OH bond. Because the chemistry changes so much, the IR becomes very characteristic around that OH. Okay? And what do we mean? For those of you in the the lab, you probably experienced what was going on with hydrogen bonding. Okay? If we look at a carboxylic acid, that hydrogen is very acidic, okay? Which means that bond that connects it is very weak. Because it is weak, that's now going to shift to lower frequencies than a standard alcohol. So our standard alcohol shows up about 3,400. Because it's now much weaker due to the acidity conjugation of that pi system, okay, it shifts to lower frequencies. And so the OH from a carboxylic acid typically centers around 3,000. That becomes problematic because a lot of other things show up at 3,000, namely all of the CH bonds, which usually means you get an overlapping of signals. We would get the OH and, let's say, OH, and we would get our peak patterning for our CHSP3s or SP2s. Those two things don't show up as separate things in the IR. They show up as one kind of average norm, and that's why you typically see for carboxylic acid a mess in that range. Okay? Depending on how clean the IR is, which becomes the next issue, you can see varying extents. Okay? So for instance, if we see the top one, that's a nice clean example because we're seeing this real broad kind of range for our OH. We're also seeing a breadth in the others, but that breadth isn't as characteristic or obvious. Right? So you have to be kind of cognizant that that breadth, as long as it's changing what you would expect a CH or a CHSP2 to look like, you probably have an OH hidden underneath that. Okay? For it to be a carboxylic acid, I would also have to see the carbonyl, and the carbonyl shows up about 1,700. Okay? For those of you being like, the carbonyl shows up for a carboxylic acid at, and I'm trying to look at the spectra to see if I can figure out what the actual range is, 1,680 to 1,700. It doesn't show up exactly at 1,700. You have to look at the spectra really carefully. Okay? So I get people all the time, oh, well, it's lower. How much lower is it? Is that an easy thing to see, or are you having to get in and be like, what is that? What's that number? I can't tell. If you got to do that, that's not worth your effort. Okay, you're spending way too much time on IR at that point. You should just be like, that's a carbonyl. Oh, there's an OH. Two together. Carboxylic acid. Done. Not this, but that's it. It's 1690. There's lots of things that can cause a carbonyl to shift to 1690, even as a ketone. So don't base it off of the exact range for a carbonyl. Recognize that there's variability within that and apply that correctly. Don't be sitting on nitpicking, oh, it's at 1701, not a carboxylic acid. That's absolute BS. Okay? Which goes back to bonds, not functional groups. Okay? I already got too riled up, so I'm going to just need to move on to the next form of spectroscopy. Our next form would be our NMR. Okay? In NMR, that hydrogen might show up at 12 ppm. Okay? That's where it's supposed to show up for a carboxylic acid. Note that we get the might. It's a carboxylic acid, which means the hydrogen's coming on and off the structure. if we're in a particular environment where it's spending most of the time off the structure, then what does the NMR see? There's no hydrogen connected to the structure, which then means we don't see the signal show up in our HNMR. Okay? That's a bit of an overstatement. The more detailed answer to that is that if your hydrogen is changing that bond energy, ranging from being super connected to not connected, okay, that means its chemical shift is different, which means when the NMR looks for chemical shifts, it sees everything from, let's call it 11.5 up to 12.5, and it counts signals. That's now taken that total count of hydrogens and spread it over a larger area, which means the peak height drops. And it drops so much that sometimes you can't see it. Okay? That's a real world system. When it comes to the exams, hell yeah, I'm going to put it on there so you can see it, and it may look stupid. It may look like I drew something on there. That's me trying to be helpful. Your hydrogen from a carboxylic acid should show up at 12 ppm. Okay? The word that gets associated with this is labile. The hydrogen can come on and off the structure. That movement is labile. Okay? Carbon NMR, we do see the carbonyl show up. We won't see the OH because the OH is not carbon. Okay? But we will see the carbonyl. The carbonyl does tend to show up a little bit lower than 200, which is what we would expect for the carbonyls of aldehydes and ketones. Okay? Why would it show up a little bit lower? What happened to the energy of that bond? Was it a stronger carbonyl or a weaker carbonyl? The aldehydes and ketones don't have resonance. The carboxylic acid does. That weakens that double bond, which causes it to slide to a slightly lower ppm value. And that's why it shifts down out of the 200 carbonyl range. Okay? With that, we're done again. Woohoo! I hope that worked. Let me know if you got questions. Have a good rest of your day.